Heisenberg, Models of Altermagnets by Volodymyr Kravchuk. Go ahead, Volodymyr.
Thank you very much. Thank you for the introduction. I will talk about magnetic properties of altermagnets, and my aim is to show that these properties, the properties of magnetic subsystems of altermagnet, can be captured by adding to the Hamiltonian specific Heisenberg terms whose orientation is respect this altermagnetic symmetry. Mainly, I will talk about the D-wave altermagnets, the simplest type of altermagnets, and in context of D-wave altermagnets, we will consider two models: the models of rutiles and the checkerboard model. We will talk not only about the altermagnetic splitting of magnon branches, but also about the number of other physical effects, such as spontaneous magnetization of domain walls or magnetization of deformed altermagnetic films, or fluctuation-induced piezomagnetism, thermal spin conductivity, and the others. And in the end of my talk, I will briefly also tell about G-wave altermagnets. And here is a picture which I generated with ChatGPT. This is how artificial intelligence sees a D-wave altermagnet. Okay, so let's start. Here you see typical examples of two kinds of altermagnets, D-wave altermagnet and G-wave altermagnet. So this is not ruthenium dioxide, this is manganese difluoride. Instead of manganese, here can be cobalt or iron or nickel. So this crystal structure is a structure of rutile. And if we ignore for a moment these red non-magnetic atoms, we see just a typical antiferromagnet of A type, meaning that we have ferromagnetic layers, one layer, second, the third layer, which interact antiferromagnetically. Why these non-magnetic atoms make this material altermagnetic? Because if you think about possible exchange interaction between next nearest neighbors within one of the layer, for example, these two or these two, we see that in one case, in the first case, the bond which connects these two next nearest neighbors goes through the non-magnetic atoms, and we can assume some super exchange mediated by these atoms. In this case, we cannot do that, so we should, for this reason, we should say that the possible exchange interaction between these neighbors and these neighbors must be different. And what is crucially important that if we consider the another sublattice, these bonds, which can gives us this super exchange, possible super exchange interaction, are oriented in 90 degrees. So in this case, in order the symmetry operation, which leaves the Hamiltonian of this system invariant, contains not only the translation by the half of magnetic unit cell time reversal, but also it must contain a rotation. In this particular case, this is a rotation by 90 degrees. Well, there are other more complicated types of altermagnets where these additional bonds are three-dimensional and the angle of rotation is different. But about G-wave altermagnets, I will talk later in the end of my talk. So here we see the very simplified model of rutile, which can be thought as a bilayer rutile. We have two sublattices, yellow and blue balls. They magnetized oppositely. The main interaction here is antiferromagnetic exchange between the sublattices. Also, we take into account ferromagnetic exchange within each of the layer, and altermagnetic properties are modeled by this additional exchange, Heisenberg exchange interaction between next to the nearest neighbors within one of the sublattices. And also here you see this symmetry. Yeah? So J1 tilde in for one sublattice is in another sublattice this Heisenberg bond will be perpendicular. Next step, we consider the classical dynamics of these magnetic moments governed by Landau-Lifshitz equation. So we have infinite set of Landau-Lewis equations, one equation for one magnetic moment. We linearize these equations on the top of ground state and find the spectra of spin waves. This is a very common procedure. I will not show here the details. The usual method is to use Holst and Primakov representation. There are other methods. Nevertheless, we found the dispersion relation. We have two bands, two magnon branches are shown here. In this particular case, anisotropy is 0, so we do not have a gap here. You see that due to altermagnetism, if these additional terms are absent, then we would have two degenerate branches. Due to this additional J1 tilde and J2 tilde, we have a splitting, which is shown here by color. And we see that within the first Brillouin zone, this splitting has a symmetry of, has a D-wave symmetry. Well, we can consider in more detail how the magnon branches behaves in vicinity of a gamma point. And when we look on dispersion relation, we see the typical behavior for the antiferromagnet. This is a splitting in magnetic field, also typical for antiferromagnet. And this is something new which comes from altermagnetism. On the next step, we proceed to continuum model. And meaning that we consider each of the sublattices as a continuous vector field. And dynamics of these vector fields are also governed by the set of two Landau-Lewis equations. And when we work with antiferromagnets, there is a general procedure which is called exchange approximation, assuming that magnetization is small, meaning that the exchange field which keeps two sublattices antiparallel is much higher than all the other effective fields in the system and much higher than external magnetic field, one can exclude magnetization from equation of motion and formulate only equation of motion for an L vector and the corresponding Lagrangian. This is a very known and quite old procedure. And what you see here in gray, this is a part of this Lagrangian formulated for an L vector for conventional antiferromagnet. And this part we derived for the D-wave altermagnet. Of course, the first thing what we can do in order to test this Lagrangian is to compute spin waves. We did it and we obtained exactly the same expression as we obtained previously in the limit of small k vector. Having the Lagrangian, we can do much more than just computing spin waves. We can consider also nonlinear solution, for example, domain walls. And in this procedure, we formulate equation of motion for L vector, but also we express magnetization as a function of L vector and derivatives. And again, this gray part is typical for conventional antiferromagnets. And here comes the new part, typical for D-wave altermagnets. And already clear that due to this differential operator, we should expect some non-zero magnetization for non-uniform solution for M. And if domain wall, of course, if domain wall is oriented exactly along nodal planes, nodal directions, which here coincide with X and Y directions, then no magnetization is expected. But if it's oriented, let's say in 45 degrees, these terms will give the maximal effect. So this is how it looks like. So this gray line corresponds to domain wall kink presented here by an L vector. So this is a Z component of an L vector. And this is the induced magnetization according to this formula and compared to the simulation which are shown here by markers. This effect can be understood intuitively. So one can show that if you consider these two domain walls, in each of the sublattices, one can show that in presence of altermagnetism, domain wall widths are different in different sublattices. And naturally, the magnetization of these sublattices do not compensate each other. So this is how it looks like, two sublattices, green and orange. This is a normal domain wall, and this is a domain wall in altermagnet. And this is an uncompensated magnetization. Altermagnetism has also influence on moving domain wall. For conventional antiferromagnet, there is a known solution for translationally moving domain wall. So domain wall in its motion keeps its profile, but experiences the Lorentz shrinking of the domain wall width. Here, angle phi determines orientation of Néel vector in domain wall. In this domain wall, in this solution, it can be arbitrary. But now, when we look on the Lagrangian, here we see that this gray part is Lorentz invariant. However, the presence of this new altermagnetic term breaks the Lorentz invariance, and of course, we should expect some deformation of this solution. In this deformation, we take into account within the first order perturbation theory, considering altermagnetic term as a perturbation. We obtain that theta, so the angle which determines this as a magnetization projection on z-axis, on anisotropy axis. It changes it's quadratic in altermagnetism, but here we have, for angle phi, we have a linear correction. This is what we obtain, and this is how it looks like. So dependence of this phi on coordinate, and this is a perpendicular component of Néel vector, a component perpendicular to the plane of unperturbed domain wall. Well, of course, it depends on altermagnetism and on velocity. And for high velocity is getting high, and of course we can expect that something dramatic should happen with our domain wall when velocity is too high. And indeed, the solution changes form when velocity exceeds some limit value. So when velocity is higher than some limited value, domain will start to precess. I mean, this magnetization, this Néel vector in domain will start to rotate. The frequency dependence of frequency of this rotation on velocity is shown on this plot. We explained this effect using the collective variable approach. The main idea of this approach is the assumption that we know the general form of solution, for example, the domain wall, but we consider parameters of this solution, for example, domain wall position or domain wall phase or domain wall width, as some parameters which can depend on time. So we substitute this solution into Lagrangian, integrate by coordinates, obtain some effective Lagrangian for collective variables. Collective variables here, these are Q's. And here we see in this Lagrangian that we again obtain some additional term which determines by our altermagnetism, and here it plays the role of some gauge field. And we consider this problem for 5 collective variables, which are domain wall position, domain wall width, domain wall phase. This term is actually also known for conventional domain walls in conventional antiferromagnets. So when we have time-dependent phase, they appear also linear correction. But this term in the middle is new. So its amplitude and amplitude of this deformation, altermagnetic deformation, and form of this deformation is the same as we previously obtained. Finally, we obtain the set of 5 quite complicated nonlinear equations, and fortunately, we see that it has a simple solution. So x is just linear function of time, so it just means that we have motion with constant velocity, and we have rotation of spins in domain wall with some constant frequency. Now we can express the rest of collective variables via velocity and this frequency, and see how energy substituted into the energy, and see how energy depends on this velocity and frequency. And we see, for example, how energy depends on frequency of rotation for different velocities. When velocity is small, the minimum of energy corresponds to 0 of its precession frequency, but when velocity exceeds some critical value, this velocity, the minimum, corresponds to some finite frequency. And this equilibrium frequency here is shown how it depends on velocity. Yeah, we see here there is some critical velocity when frequency start sharply differ from zero. And this is how this limiting velocity depends on altermagnetic parameter. For vanishing altermagnetism, it just coincides with the maximal speed of magnons. Okay, so we learned from the previous part that non-uniformity of magnetization of Néel vector can lead to magnetization in altermagnets. But the domain walls is not the only source for non-uniformity. The non-uniformity can appear due to bending. So if we consider this kind of cylindrical surface, we can compute how theta, this is the angle between normal direction and the Néel vector, how it deviates from normal direction. Yeah? And we can show that this deviation is proportional to the gradient of curvature, and we can compute the corresponding altermagnetically induced magnetization, which is approximately tangential to the film and also linear in gradients of curvature. So here we can consider this on more specific example of sinusoidal deformation. Yeah? So this on the higher plot, you see the distribution of Néel order parameter. And on the places of bending, we have a competition of two tendencies. We have, of course, exchange, which wants to keep all Néel vectors parallel, but we also have easy normal anisotropy, which want to keep all of them parallel perpendicularly to the surface, parallel to the normal. Of course, here appears a competition which results in deviation of Néel order parameter from the normal direction. And due to this deviation, as we considered previously, there appear a magnetization, which is shown here on the lower plot. And for this specific geometry, when we have sinusoidal rippling, we see the total magnetic moment per period is not zero. So it's directed, in this case, up, yeah, and it's not zero. And here we compute how the total magnetic moment depends on Q and amplitude and wave vector of the deformation. The sign of this magnetic moment and its amplitude depends on orientation of the deformation. So it vanishes, that even appear if this wave vector of deformation is along the nodal planes, and the maximum value we see when this Q vector is along this altermagnetic diagonal terms. Yeah. This is how we expect that it can be used. Well, there is a big problem of detection of antiferromagnetic domain walls. Already we know that due to altermagnetism, domain wall possesses some magnetization. So here we compare a planar geometry and ripple geometry. In planar geometry, we consider some domain structure shown here by color. So this is the end vector, perpendicular component of Néel vector. And here is the corresponding magnetization of domain walls. Yeah, it's a strongly localized on domain wall. Moreover, it has an alternating sign, meaning that stray field will be very much concentrated, localized in this region, which makes the measurement quite complicated. But when we make the rippling, there appear magnetization signal also from the domain, not only from domain wall itself, it's still here, but also from domain. And theoretically, due to such a kind of rippling, one can see the domain structure also in antiferromagnet. Let's consider another model. This is a checkerboard model. The only difference is the different orientation of the altermagnetic bonds. So in each of the sublattices, we have additional exchange interactions. But in one interaction, these bonds are oriented along x-axis. In the another sublattices, they are oriented along y-axis. This model also results in D-wave type of splitting of magnon bands, but it's also convenient for a number of other investigations. For example, this model is convenient to investigate the influence of external strain. For example, if we assume some external stress along x-axis, due to change of the distance between the atoms, we can expect that Jx tilde will become larger, and Jy tilde will become smaller. And so here in this model, we have a direct connection between external stress and altermagnetism. For this model, we computed the piezomagnetism. So we computed magnetic moment based on thermodynamical definition of magnetic moment. So this is just derivative of free energy on applied magnetic field. Free energy for gas of non-interacting bosons is known. So magnons are bosons, and this is a magnetic moment, and we can compute the magnetic moment density. And we can show that this density depends on difference on these altermagnetic strengths in along x and y direction, meaning that we need these terms to be different, what can be achieved by applying the external stress. And eta here we called the piezomagnetic constant, and here we analyzed how this eta depends on temperature. So this moment is generated by fluctuation of magnons, in contrast to another magnetic moment which can appear from ferrimagnetism. You know, when we add to the Hamiltonians Heisenberg-Landau terms, which determines the equilibrium value of magnetization for each of the sublattices, we can see that if we apply a strain and these terms becomes different, two magnetic moments amplitudes, their amplitudes becomes necessarily different. And we have also some kind of ferromagnet also, and this leads to the magnetic moment. But this effect, it behaves very much differently in temperature. It's not related to fluctuations, and its behavior is different. Yeah, here we made some estimation for low temperature. For this we did three-dimensional generalization of our model. So we consider just a stack of layers with ferromagnetic interaction between them. In this case, we can have the ordering even without anisotropy, meaning that we do not have gap, and that is why the dependence here is just power law. Additionally, we consider the temperature spin conductivity. So we considered the spin current, which can flow in response to applied temperature gradient. So in the relaxation time approximation, we computed the conductivity, this temperature conductivity, obtained the tensor. So if you know dispersion, we know everything. And for this effect, we do not need to apply the stress. It's just a property of D-wave altermagnet. And also it's present for root tiles as well. This is how the spin conductivity depends on temperature. The specific property of checkerboard is possibility to generate a Berry curvature for magnons. And this is how it works. For this case, we should consider easy planar checkerboard model, or we can introduce easy planar anisotropy, or instead of anisotropy, we just can add a magnetic field. It will make the spin flop phase the ground state of the system. In this case, we already have a splitting between two bands. They are not degenerate, except the boundary of the first brilliant zone. In order to remove degeneracy on the boundary, we additionally add DMI interaction, DMI vectors shown here by green color. And in this way, we remove degeneracy everywhere except the midpoints of the edge of brilliant zone, the points X, Y here, and we still have a gap here. And this gap is completely controlled by the altermagnetic parameter. So tuning this parameter, we can control the distribution of Berry curvature within the brilliant zone. If this parameter is small, so gap is small, the Berry curvature is concentrated near these midpoints, and when it's getting larger, it's distributed over the first brilliant zone. So the upper and lower plots here corresponds to upper and lower Magnum branches.
Volodymyr,
Okay.
you have 5 minutes, including questions.
Yeah, thank you. As a consequence of non-trivial topology of magnets, we computed thermal Hall conductivity of magnets and see how it depends on temperature and magnetic field. And also we obtained the edge states. Yeah, then I just briefly say that situation with G-wave altermagnets is analogous, however, more complicated. We need to consider more complicated crystal structure, introducing the three-dimensional Heisenberg bonds. And as a result, we can show that for, let's say, chromium antimonide, which is a well-known G-wave altermagnet, we obtain the splitting of Magnum bands. And this splitting within the brilliant zone has the same symmetry as the G orbital of hydrogen atoms. That is why it's clearly a G-wave altermagnet. Yeah, here my conclusion. So I want to reduce it only to one statement that behavior of magnetic subsystem of altermagnet can be described using additional super exchange Heisenberg terms. And here is the list of predicted physical effects, which in this model we can predict. Here's the list of our publications, and especially I want to thank all my co-authors listed here on the right, and especially to Konstantin Yershov, with who contributed to all of these projects. Thank you very much.
Okay, go ahead. There's a question here.
Volodya, this is Sergey. I would like to ask the following question. You mentioned that spin conductivity dependent on temperature. Are you talking about spin-Seebeck effect?
This is more like Nernst effect. I mean, we have the spin current in response to temperature gradient. However, in contrast to Nernst effect, this current not necessarily flow perpendicularly to the gradient. It can flow in different directions depending how this gradient is applied with respect to crystallographic axis.
I see. Thank you. And I would like just to update myself. I know that in general, the definition of spin current has some controversies because in contrast to charge, there is no charge conservation. Is there some progress in how to use the correct definition and so on? Thank you.
No, I think we did not. Well, I am afraid I'm not even aware about this problem. So what we did here is very simple relaxation time approximation, which I learned from, say, Ashcroft.
Are there any online questions?
May I ask some question?
There is a question back there. Oh, there was an online? Okay, great. Go ahead. Yuri.
Okay. The specific feature of altermagnets is the anisotropy in the momentum spin space. So do you see some asymmetry like is usual transfer properties, for instance, or your wall domain wall motion and so on? Specific asymmetry.
Yeah, well, if you talk about domain walls, these properties which I described here, they very much depend in which direction domain wall moves. So here we consider the domain motion in the direction when altermagnetic effects are maximal, meaning that this is the direction of these diagonals in which we have these altermagnetic bonds. If the direction will be changed by 45 degrees, the effects will vanish. So yes, there is a strong
So
So
another direction,
anisotropy is respect to the motion of the magnets.
another direction, it looks like its behavior looks like its usual antiferromagnet.
Yeah.
Okay.
Okay, we have time for one more quick question at the back then.
In your model, you have a differential term specific altermagnets. Do you expect another term possible specific for altermagnets in the Lagrangian or Hamiltonian? I'm wondering because in the first talk we have heard that there are some features.
Can you repeat the last sentence? I do not hear clear. The last sentence, please.
Do you expect other terms than differential terms for altermagnetic description of altermagnetic behavior magnetization? For instance,
non-differential.
Are you referring to his Lagrangian with a
Yeah,
second order?
yeah.
If he's referring to any other terms in your second order derivative in exactly
Well,
the last term.
we did not obtain. So this is what we obtain. So in this model, when we model the altermagnetic properties by this Heisenberg terms, one cannot obtain something else. But
The answer is yes, but it's higher momentum, closer to the real zone. Okay, so I think we have to move on.